Right, the aim of this PowerPoint is to teach you guys about transistors and these things called field effect transistors. So there's a little PowerPoint you can go look at which tells you the facts you need to remember. I'll do a couple of demonstrations to show you what I'm talking about as well. This page here just tells you what the examiners want you to learn about. Okay, I don't need to read it out to you, but basically what they look like, what the legs do, the fact that you can join two of them together to make a thing called a Darlington pair, the fact that you can find them ready packaged onto a chip, you get lots of them on one chip, and then you need to know there's two main categories, bipolar and field effect. Okay, right, first things then, they do two jobs. Doesn't matter if it's a transistor or a field effect transistor, and Darlington pairs actually, they always do two jobs. And if you ever get a question that says name one job you could use a transistor for, say one of these. Acts as an electronic switch, I'll explain that in a minute, or it can be used to amplify current. You should know that amplify means to make bigger. Okay, next thing up then, what do they look like? You've probably used one in your coursework. They could look like that, like this, like that, or anything in between. Generally, if it's got three legs, it's probably a transistor. Sometimes they have a way of telling a particular leg apart, like they might have a little tab on there, but normally you can't guarantee which leg does what. You have to look it up in a data sheet. You won't get asked that in the exam, so don't worry. You do need to know what each leg does, and you need to know the symbols, which are on the next page. Just one thing I should mention actually, I have seen this in a question before, the bigger ones have like a metal bracket attached that you can screw a bolt through and bolt it onto a piece of metal to kind of suck the heat out of them, because the bigger ones get quite hot with all the current that they switch on and off. Anyway, that's what they look like. This is what the symbols look like. Bipolar transistor is the most common type, that looks like this, and field effect transistor looks like that. Names of the legs, there's no easy way of remembering, well there's a sort of easy way of remembering, I'll tell you about it just now. It's easy to explain with a diagram, but this is what the legs are called. This one on the left is the base, this is the collector, this is the emitter. If you imagine in a circuit you'd normally have positive at the top, and you can imagine that that wire goes up to positive, so it's collecting the energy from the battery. Normally things that you're trying to switch on go onto this leg and then go to negative, and it emits energy, emits electricity to turn on whatever you're trying to do. So that's why it's called the emitter. And then the base, there's no easy way of remembering that. I'm not going to lie to you, just remember it's the one on the left. Field effect transistor, just because they like to confuse you, they give all three of the legs a different name, which is awesome, and that is those. Top leg is the source. I like to think of it as sourcing its energy from the battery. Drain, whatever you want to use would drain energy, and you'd connect it to there. And the gate, when you see how they work as a switch in a minute, the gate, imagine you open a gate to let something through, don't you? And that's why this leg is called the gate. Hopefully it'll make a bit more sense in a minute. Try and remember those names when I show you the demonstrations. Okay, I'll come back to this PowerPoint in a sec and we'll do a demo for you. So, go in the circuit wizard. Here is transistor. That is the bipolar type. Just to prove it to you, you've got base leg, collector and emitter, and I'm going to wire one up for you just into a typical transistor circuit, the circuit that you're probably more than likely going to get if you get a question in the exam. I think every time I've seen it, it looks like this. Right, here's positive, that's going to go to my collector so the transistor can collect energy from the battery. My emitter is going to go to whatever I'm trying to turn on, which in this case is an LED. Obviously I've got a resistor there, you should know what that's there for, to protect it from too much current. My LED needs to complete the circuit, so it goes back to the battery, so I've got a circuit here. I'm going to make a potential divider, which you should have learned about already, by connecting a resistor to positive, the other end of the resistor to another resistor, and that resistor to negative, and of course making a wire out in the middle where my divided potential comes out. I'm then going to join that onto the base of the transistor. Do remember, This is actually a resistor. It's a light dependent resistor, so you might think of it as a light sensor. Try and get in the habit of calling it an LDR, light dependent resistor. Alright, let's show you what happens. I press play. LED's not lit at the moment. I've got no light at all. As I shine light, nothing's happening with the LED, nothing's happening, and then at a certain point the LED starts to come on. Now you notice it will come on very faded at first, and then as I get more light there'll become a point where it's fully on, and it doesn't matter how much more light I add, the LED is still fully turned on. I'm going to try and explain to you what's going on now and how this works as an electronic switch, and to do that I'm going to get a voltmeter. If you remember about voltmeters, how do you connect them? You connect them in parallel. So I'm going to measure the volts here and across there in parallel, and I want you to look at the voltage readings we're getting. Okay, so at the moment I've got 725 millivolts, which is about 0.7 of a volt, not a great deal, and my LED isn't turned on. And if I keep increasing the light level, because it's a potential divider, my voltage is going up. It's now 1 volt just over, 1.13, so on, 1.4, and at about, there we go, just over 2 volts, you can see that my LEDs start switching on. Now what you've got to understand is how that's happening. It's because this thing is acting as a switch. Okay, if I look at current flow, what is happening is my LED is actually getting its energy, its current, following where my mouse is going. It's getting it through this pathway here. Okay, imagining through here, and it's getting it straight out of the battery. However, because this is what the transistor is, what's called a semiconductor, it only allows energy to flow through it when it gets a certain voltage on this leg here. Okay, for this particular setup, it's anything over about 2 volts allows it to start conducting. Can you see if my voltage is below 2 volts? I haven't got any lines moving here. I've got nothing conducting. The transistor is not conducting. There's no path for my LED to get power, therefore it doesn't turn on. As I change the voltage here with my potential divider, when it gets to 2, the transistor switches on, energy starts flowing. You can just see it starting to flow, but it's not enough to light the LED. And obviously as I get brighter and allow more voltage through, the more this conducts. So it's acting as a switch, but remember, it's not a switch that you're pressing with your finger. It's a switch that's being activated by another part of an electric circuit. Okay, and that is a really, really core principle. You might think, what's the point in that? I could just have a button. Well, sometimes you don't want a button. Sometimes you actually want to sense things like light or temperature, pressure, and you can use this circuit as a sensing circuit. This would be a night light. Okay, it would actually be the opposite of that. This would be a light that comes on as it gets light outside. I could actually make the reverse of that. I could make a night light, and all I'm going to do is swap these two around. So I'm going to put my resistor on the top and my LDR on the bottom, and what we should expect to see now is when I make it darker, the light should come on. Okay, so I'm in light at the moment, my voltage changes above 2 volts and my LED starts coming on. Okay, and it's because the transistor is switching on when it gets a signal on the base. Alright, I'll emphasize that again. It only switches on and opens up a path through it when it gets 2 volts or more on the base leg. That's all you need to know. It may say a different voltage in your revision guide. To be honest, it doesn't really matter what voltage it starts to turn on at, so long as you get the idea that a particular voltage is needed on this leg to allow that to conduct. I know I've said that about 20 times, I do apologise. Right, that is a transistor acting as a switch. Go back to the PowerPoint, see if you can remember. I said the second thing it does, it amplifies current. Okay, current being the amount of electricity available. I can prove that to you with an ammeter. Okay, get the ammeter. I'm actually going to get 2. So I'm not going to measure volts anymore. Remember, an ammeter always goes in the flow of the electricity. So I'm going to connect one here between my potential divider and the transistor, and I'm going to connect another ammeter. I've got to make some room for it between my LED. Okay, so I'm measuring the amps going in and I'm measuring the amps coming out, and if it's an amplifier you'd expect it to be bigger. So press play. Now just that. Ignore the fact it says minus, it's just because I've connected my amp meter the wrong way around, just because I know some of you will go, oh what? I'll flick it the correct way. So you could just ignore everything I said for a second there. Anyway, right, so I'm reading 26 microamps. If you remember your conversion, micro means times 10 to the minus 6, so that's like 0.00026 amps, a very small number. This is only 0.008 of an amp, right? Trust me, if you don't know your maths, 8 milliamps is always going to be bigger than 26 microamps. Right? Go do the tutorial on standard form if you don't believe me. But what I'm proving here is I'm getting amplified currents. Why is that important? It means you can drive something more powerful from a very small signal. So try and imagine it the other way around. If I, for instance, put a speaker here. Now unfortunately this circuit's not going to do anything because Circuit Wizard's not smart enough, but I'm just going to put the components in to explain to you what I mean. I'm going to go get a microphone as my input component. Okay. It's not actually got a microphone. I'll use a crystal, which would work the same way. Right. This would be like a speaker system. You talk into it and it amplifies your voice and makes it come out louder. Now, if you know how a microphone works, when you speak into it, it makes a little cone vibrate back and forward, which moves a magnet, and that magnet generates a tiny, tiny, tiny amount of current, a tiny little electrical signal, which you can feed in through a potential divider to your transistor. Now, if you didn't use a transistor and just tried to use that tiny, weedy little electrical signal to make noise out of the speaker, it wouldn't have anywhere near enough power to make the speaker vibrate and produce sound. If you run it through a transistor, it preserves the same signal that you sent by speaking, as in your voice, but it adds to it and makes it the same signal, just bigger, with more current behind it, and therefore you might have enough to make a speaker vibrate and make a noise. Okay. This won't do anything because it doesn't know I want it to be a microphone, but if you didn't understand a lot of that, just remember the fact you can use it to amplify current. That's all you need to know. And remember, it can be used as a switch. To be honest, the questions in the exam paper are not going to be more complex than that. Right, one other thing I wanted to show you, Darlington pairs. I'm going to go back to my previous layout, get rid of the ammeters, so I'll just backspace a bit. Okay. Right, a Darlington pair is a bit of a stupid name. I think the guy who invented it was called something Darlington. That's usually how it goes. But it's nothing more complex than two transistors stuck together. Right? You have one transistor, I copy and paste, to make another, driving, rather than connecting to your output, you connect it to the base of another one, and then you connect the emitter of the second transistor to whatever you're trying to turn on. Both of these legs are collectors, so they can both collect energy from the battery. Okay. Now, you'll see this works in the same way, but what you might notice is it's very hard to get a fading LED now. This has done two things. Okay, it's made my transistor switch a lot quicker, as in rather than sort of gradually turning on and then being fully on and it taking a lot of light to affect that change, it's coming on with a relatively small difference in light. It's made my transistor not quicker but better at switching. Okay, that's one thing they do. I've set that on the PowerPoint. The other thing it does, if I go and get my ammeters again, you'll see it's probably made, well, there's no point bothering to do it, but just trust me on this one, it increases the amount it amplifies by as well. It makes sense if you think about it. If you amplify something once and then amplify the amplified something, you get something even bigger proportionately. That factor is called gain, by the way. You don't need to know it, it's not in the spec, but gain is how much you amplify or make a signal bigger by. Okay, using two of them makes it bigger. That's the whole point of the Darlington pair. One thing you need to know, and that will be in this, in the PowerPoint, the legs are labelled the same. Remember, both collectors, this one and that one, end up going to the same place, so you just replace them with one connection. You have one emitter because the other emitter is tied up here, connected to the base of the second one, and you have one base. So overall, you've still got just 3 connections to plug in, and for that reason, you can quite often buy them ready assembled in one case. Right, you could make them out of 2 separate transistors, or you can buy a ready-made Darlington pair in a box, because as you can see from that diagram, there's only 3 connections, so it fits in a 3-legged box. There's your 2 benefits: higher current amplification and a more instant switch than just using one and the same. Right, final thing you need to know, I'm not going to bother modelling this, I'm just going to show you with some pictures. The exam board says you need to know that they're available on a chip, quite simply like that. It's an 18-leg chip. Typical one is a ULM2803. I don't think you even need to bother remembering the name. Inside, ignore the fact they don't look like transistor symbols. You've just got to assume there's a transistor in each of these lines here, and these are just diodes to protect each transistor in case you connect them up back to front. But basically, they're wired up like that. Pins 1 to 8 are the bases. You've got 8 transistors on one chip here. These are each of your 8 base legs. Pin 9 is ground. That's just, you don't really need to know why that's there, just it's useful to keep the circuit tied down to 0 when it's not being used. And pins 9 to pin 10, if you look at this, it connects to every single transistor with one wire. Okay, that is all the collectors wired together, and therefore pins 11, 12, 13 all the way to 18 are the individual emitters for each of the transistors. To be honest, don't even worry about how it's connected up. They're not going to ask you to draw it. They might just ask you, why would you want to buy 8 transistors on a chip? And those are your reasons. It's going to save you space. It saves you soldering, because rather than 8 collector legs, you've only got 1, because it's replaced all by pin 10. It's easier to replace if a transistor blows, rather than having to unsolder it. A chip you can fit into a socket. It obviously keeps costs down. It's actually cheaper to buy 8 of them on one chip than it is to buy 8 individual ones. And another sort of benefit, they've got built-in protection, which you would have to add on yourself if you were going to make it with individual transistors. But main thing is save space and it's cheaper. Right, so we've done a lot there. Let's just recap what we've learned. How and when to use a bipolar transistor. Well, we know how to connect it up, I showed you that, and when you'd use it if you wanted to activate an electronic switch, so from a sensor of some sort, or if you wanted to amplify current to make a bigger signal. I'm sure you can recognise the symbol. It does say photo transistor. I will just touch on that very quickly. If we look at the symbol for one of these, the photo transistor looks exactly the same as this, but it has 2 arrows pointing at it, which means light is shining on it, a bit like an LDR. So we've done photo transistors. Identify the base, emitter and collector, done that. Draw the circuit diagram, understand the use of a Darlington pair. The circuit diagram is just 2 of them drawn together, easy. Be aware that Darlington pair can be packaged as a single transistor. I told you, you can get them in one box. Be aware that you can get Darlington driver transistors packed as an array on a single chip. I showed you that. Field effect transistors, know how and when to use a field effect. I'll quickly talk about that with another demonstration. Recognise the symbol, yeah, and identify the legs. Right, field effect transistor, I didn't show you it, but you basically wire it up exactly the same way as you would do a normal transistor. Here's one, N-channel MOSFET. That MOSFET, by the way, stands for metal oxide semiconductor field effect transistor. Yeah, fascinating. Just try and remember field effect transistor. Okay, so you've got top leg, drain, bottom leg, source. Okay, the drain is draining the energy from the battery, the source is giving it to whatever you're trying to turn on, and then the gate which opens up. You open the gate to allow energy to flow through it, goes to your sensing potential divider. Okay, and just to prove it, there you go, as it gets dark or light even. Okay, this one works the opposite way around. I guess you just need to know why you would use a FET, a field effect transistor, instead of a bipolar one. Generally, FETs are able to switch more current, they're more powerful. Right, so you can control more powerful devices here. Usually you'd use a FET with a motor, because a motor uses a lot more current than an LED does. So if you see a circuit a bit like that with a motor, chances are, here's a motor, chances are you're looking at a field effect transistor. And another reason you'd use them is a bit like the Darlington pair arrangement, switched quicker. A field effect transistor switches quicker as well. It comes on a lot more instantly. Okay. Now you may be thinking, why, Mr. Whitmer, is the motor not turning? This is a side topic, but you should know that you never need to put a resistor in front of the motor. The motor doesn't need protecting from too much. Okay, here we go. And as it gets dark, my motor turns. Okay. Cool. Right. That's it. We've done field effect, we've done bipolar transistors, and we've done Darlington pairs. You need to understand these and be happy with them, because a lot of the other topics we're going to go on to later on are all based on these three things. Okay.